So the most dreaded topic that most young data scientists usually fear is linear algebra. And I totally get it because the relation between the numbers, geometry and all that stuff is quite scary initially. So today I will try to explain it in a very easy manner that how I understood this. So let's start with the most basic concept, linear algebra. So I always understood it as the relation between numbers and geometry. A simple relation between numbers and geometry. Now, it's better if I explain with an example. Imagine if you are standing at any point O, origin, and someone tells you to take a step in the east 2 units and in the south 3 units. So this is how you picture it in your mind, right? You make a visual representation of this whole concept. But in your in on paper, how will you say it? 2 units to the east and then 3 units to the south. No, just see it very, very carefully. What are these? These are scalar quantities, the numbers, and these are what? The directions. Now, if I give you 2 and 3 like this, and east and south like this, individually they do not make any sense. 2, 3, and east, south. What does it make sense? But the moment you combine them, you know what I'm saying. 2 units to the east and then 3 units to the south. You reach the final target location where you get a reward. Now, how did you map or build the relation between them? This is what linear algebra does. It maps the relation between the numbers and the geometry. So whatever in your mind, how the numbers are stored and how the directions are stored, the map or the bridge connecting them, this is what the linear algebra builds. And that's what's very important. Just think of it like GPS coordinates. You simply using units or simply using directions is not powerful enough. But when you try to map them using linear algebra, you know where you want to find the shortest path or any type of thing. So this is how I understood the linear algebra in a better way. Now, that being said, I will try to move forward with the basic concepts and try to explain it. This is just an introductory video. I try to explain this in the most easiest term, so the fear of linear algebra can vanish. So the next concept, vectors and vector spaces. Most people think vectors are it's a tensor quantity with a magnitude and a direction in a space. Yeah, it's right. But when they see vectors represented like this, 2, 3, or 1, 0.1, they get it's already scary enough. So how I like to define it was that it's nothing but just a fancy name for a list of numbers. Nothing humongous, no tough terms to explain. Just a fancy name for a list of numbers. For any type of list of numbers. 100, 200, and 3. Any name for this fancy list of numbers is called a vector. And but what does it signify? Nothing. It can signify any type of information. And this information is dependent on the user. For example, if you are a landlord and you are using a three-dimensional vector with 100, 200, and 3, you are free to set what they mean. 100 means maybe the rent of one room, 200 means maybe the rent of the second room, and 3 means the number of bathrooms in the flat. So you are free to choose what this dimension mean. So this is just nothing but just a fancy name for a list of numbers which signifies something. And what linear algebra does, it it takes the advantage of this meaning. When it shows 1, comma 1, 2 in a vector form, it's just a fancy name for a list of numbers. Okay, it's just a list of numbers, and the information that it stores here is how much you need to move in x direction and how much you need to move in y direction. Move 1 unit in the x and 2 units in the y. You get to a point. This point is what linear algebra is saying that go to this point. So whenever it says 1, 2, nothing to worry about. It just means that go 1 unit to the x and 2 units in the y. I'm just saying in the form of a list of numbers, nothing else. 1, 2, 3, a three-dimensional numbers in three-dimensional space. Go to this point. Nothing fancy. So this is all just a hoax, and that vector is very tough to explain. Nothing like that. Sorry, it's taking too much time. I'm new to this tab. Okay. Now the second one is vector spaces. Now you know what vectors means, right? A fancy name for a list of numbers, and these list of numbers can signify anything on what the user wants. Vector spaces. These vector spaces are simply a collection of vectors. Collection of any number of vectors, any type of vectors, collection of any number of vectors, any type of vectors is just simply a vector space. That is, if you define a vector as AB, where A belongs to a real number, I think this notation is too powerful, where A is a real number and B is also a real number. So what does this signify? You can put 1, 2, you can put point 0.1 minus point 0.2. These are all vectors, right? They can signify anything. Here, for example, if you are seeing it from a linear algebra point of view, it means on the I cap move A units, on the J cap move B units, right? So some point in the two-dimension space. This is what the vector space is showing. So this means it covers the whole two-dimension plane. So the whole two-dimension plane here becomes what? Our vector space here. And this is how a vector space is defined. So it is nothing but just a collection of all the vectors. Imagine you have too many matchsticks and each matchstick is a vector. So when you collect all these matchsticks from all over the world, you make a whole vector space. Okay, nothing scary or nothing too humongous to understand. But one rule I would like to clarify here that the vector spaces have. Vector spaces always have these two properties: scalar multiplication and vector addition will always give another vector of the same vector space. What I mean with this is, imagine you have this vector space, right? The whole two-dimensional vector space AB, where A is a real number and B is also a real number. Okay? So this is the whole vector space. Now, if I take any two vectors or three vectors or any four vectors, let's take two vectors for simplicity. If I do a vector addition, why I'm calling this vector addition? Because I took two vectors from the vector space A1, B1 and A2, B2, where A1, B1 and A2, B2 both are real numbers, right? If I do a vector addition, then it might give me a result A3, B3. And this A3, B3 is another vector of the same vector space or on the same two-dimensional plane. Then this property is satisfied. And another property of scalar multiplication. If I take any vector like this, A4, B4, and multiply it with the scalar quantity lambda, which can be any real number, then lambda A4 and lambda B4. If this vector is another vector of the same vector space like this, if both these properties are satisfied, two vector addition and a scalar multiplication, the results both lie in the same vector space. These are the results and they both lie in the same vector space from where the parent vectors belong. Then these properties when are satisfied, then also vector spaces are valid. So these properties are always followed from the vector space definition. This is one extra point that I like to note. Now this is complete. Now I'd like to move to the next topic. Before that, I will share with you about linearly about basis vectors, which are also sometimes confusing for people. No. Uh, Basis vectors. Before this, I think I should tell you about linearly independent vectors, popularly known as Li vectors. What are these? Imagine you have a vector space on the two-dimensional plane, the form of AB, where A belongs to real, B belongs to real. By now you must have remembered it. Okay, this is a whole vector space, collection of all the matchsticks. Try to remember it like this. Now, if you take any two vectors or any three vectors or any four vectors, any number of vectors, and you do a linear combination of them, what is if we take any vectors v1, v2, v3, each are in the form of some ai, bi, right? So if we take three vectors and do a linear combination, what I mean by linear combination, scale and add. See, scaling and adding are the only two properties that most of the vector space signify. So if we do scaling and addition, that is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. This is a linear combination of all these vectors. We took this vector, scaled it, this vector, scaled it, this vector, scaled it, and did a vector addition to give some this vector. Okay. And these alpha 1, alpha 2, and alpha 3 are arbitrary value. So we can set them to any values we want, right? So we can get this vector also, this vector also, this vector also based on different values of alpha 1, alpha 2, and alpha 3, right? Now imagine if all the linear combination of these vectors can uh, uh, can never form this v4 vector. If they never form this v4 vector, let this v4 vector be this. This can happen due to some constraints, like if v1 components are restricted in a particular region, v2 components are restricted in a particular region, then it might happen that v4 will never be formed. So if that is the case, alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is not never equal to v4. Now imagine if I put v4 on the left hand side, what happens? Alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 minus v4 is never equal to 0, right? Now, this minus v4, what is this? Plus minus 1 into v4. And minus 1 is what? A scalar quantity. So I can I write it like this? Alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4. Because here it is minus 1. In some other case, it can be 2, 3, 4. So it can be take any scalar values. It's never equal to 0 because right hand side when I took there, it became 0, right? So this, what does it say? That this will be never equal to 0 unless and until alpha 1 is 0, alpha 2 is 0, alpha 3 is 0, unless and until all become 0, this will never be equal to 0. So this is what the linear independent vectors means. By any linear combination of vectors, if you can never put together another given vector, these set of vectors will always be called linearly independent vectors. But if it's possible to put them equal to 0 using some non-zero values, at least one non-zero values at these places, then it is called linearly dependent vectors called LD vectors. I know it has become a bit messy, but I will try to summarize it at the end. So this is what the linearly independent and the linearly dependent vectors mean. Now, why is it important to understand matrices? Because in the before the matrices, I want to tell you about something called as basis vectors. Just a simple definition. They are nothing but linearly independent vectors. That is, if we took any linear combination and we can't make another vector, then these set are become linearly independent vectors. So any linearly independent vector set that can span. Span is nothing but a fancy word for linear combination, which we just saw. Alpha 1 v1 plus alpha 2 v2. This is just a span. So if linearly independent vectors span the whole given vector space. Imagine if you have a given vector space of two-dimensional plane. So if we took these vectors, these linearly independent vectors, did a linear combination, scale and add, scale and add, scale and add, and it always gives any vector of this vector space. Then for this vector space, these linearly independent vectors will be called basis vectors. So these are just like from these vectors, make this whole two-dimensional plane. So this becomes the basis vector, but they should always be linearly independent with respect to each other. And this is the vector space form. So these vector space parents are these Li vectors. This is called basis vector.